What if the universe you perceive is a grand illusion? Not a trick of the mind, but a profound deception of scale. You feel the solid ground beneath your feet, a gentle curve of a planet. You see the stately procession of the moon, the distant, silent fire of stars. This is the cosmos as we know it, a place of breathtaking, predictable grandeur. A universe governed by a law of such profound elegance and sweeping power that it feels less like a formula and more like divine thought. This is the universe of Albert Einstein. His theory of general relativity is the supreme architectural blueprint of the cosmic cathedral. It describes gravity not as a mysterious force pulling us down, but as the very shape of existence itself. Imagine space-time as a vast, flexible fabric stretching across all of eternity. A star, a planet, even your own body creates a depression in this fabric, a gentle cosmic well. What we call gravity is simply the consequence of following the curves. The Earth doesn't pull the moon. It tells space-time how to bend, and the moon in its turn follows that curve in a perpetual silent waltz. It is a theory of absolute perfection. Its mathematics predicted the bending of starlight around the sun, a whisper confirmed in 1919, transforming Einstein from a mere scientist into a global icon. It predicted the existence of gravitational waves, ripples in the cosmic fabric itself, a prediction so audacious it took a century for our technology to finally hear those faint echoes from the collision of black holes a billion light years away. Every time you use your phone's GPS, you are relying on Einstein's equations. They must account for the subtle warping of time caused by Earth's gravity, a correction without which the system would fail in minutes. This is a theory that works. It works with a precision that borders on the miraculous. It is the language of planets and stars of galaxies, pirouetting in the dark of the entire universe, expanding from a single fiery origin. It is a smooth, continuous and deterministic vision of reality, a reality where, if you know the starting conditions, you can predict the future with utter certainty. It is one of the two great pillars holding up all of modern physics, a masterpiece of the human intellect. And it is completely fundamentally, hopelessly wrong, or at least it's only half the story. To find the other half, you must abandon the sweeping curves of the cosmos. You have to shrink. You must journey down past the familiar world of atoms, past the nucleus, into a realm so fantastically small and bizarre that all the rules of our everyday reality shatter into meaningless dust. Welcome to the quantum world. This is the domain of the other great pillar of physics, quantum mechanics. And if Einstein's universe is a majestic, predictable cathedral, the quantum realm is a chaotic, shimmering, probabilistic fever dream. Here there are no smooth curves, no certain paths. There is only a seething, violent foam of possibility. Down here, a particle like an electron doesn't exist in a single place. It exists everywhere it could possibly be, all at once, a ghostly cloud of potential, until the moment we dare to look at it. Only then, under the harsh glare of observation, does it reluctantly snap to a single position, as if annoyed at being disturbed. This is a world where particles can tunnel through solid walls, a feat as impossible in our world as walking through a mountain. It's a place where empty space is not empty at all, but a roiling cauldron of virtual particles flashing in and out of existence in pairs, borrowing their brief moment of being from the universe itself. This is not speculation. This is not a wild guess. Every laser, every computer chip, every nuclear power plant is a testament to our mastery of these seemingly insane rules. Quantum mechanics is the most successful, most rigorously tested theory in the history of science. Its predictions have been verified to an astonishing number of decimal places, making it the most accurate description of reality we have ever conceived. It is the language of the infinitesimally small of the forces that bind matter together, of the light that travels across the universe to reach your eye. It is a world of discrete packets, or quanta, a world that is fundamentally jittery, uncertain, and probabilistic. A reality where God, as Einstein famously lamented, appears to play dice with the universe. For nearly a century we have lived with this schism. We have treated physics like a broken kingdom ruled by two powerful rival monarchs. General relativity, the king of the large, governs the graceful dance of celestial bodies. Quantum mechanics, the queen of the small, rules the frenetic, unpredictable world of particles, and for the most part they reign in separate territories. The gentle gravitational pull of a single proton is so laughably weak, it has virtually no bearing on its quantum behavior. The quantum jitters of a planet are so minuscule, they are completely washed out by its immense mass. The two theories simply don't need to talk to each other. They can exist in a state of benign neglect, each a perfect description of its own domain. But there are places in the universe where this fragile truce shatters. Places of such unimaginable extremity that the domains of the large and the small violently collide. Places where the king and queen are forced into the same room, and their languages are so utterly incompatible that they descend into screaming, nonsensical chaos. To understand the great war for the fabric of space, we must travel to these frontiers of existence. We must journey to the two places where our current understanding of reality collapses. Our first destination is a monster. It is a place where gravity becomes so overwhelmingly strong, so pathologically dominant, that it tears the fabric of space-time itself. We must go to the heart of a black hole. As a massive star dies, it collapses under its own immense weight. Gravity runs rampant, crushing matter out of existence, squeezing a sun many times the mass of our own into a region of space smaller than a city. The gravitational field becomes so intense that a boundary forms the event horizon, a point of no return from which not even light can escape. General relativity describes this journey with terrifying clarity. It tells us that once you cross the event horizon, all paths lead in one direction downward toward the center. Space-time itself flows inward, faster than light, dragging you toward the ultimate abyss. And at the very center, Einstein's beautiful equations deliver a verdict that is pure madness. They predict a point of zero volume and infinite density. A singularity. It is a word that physicists use when their mathematics break down. It is a prediction of an infinity, a place where the curvature of space-time becomes endless, where the laws of physics, as described by relativity, cease to have any meaning. The elegant cathedral of Einstein's universe collapses into a single nonsensical point, but nature does not permit infinities. An infinity is a signpost, a warning from the universe that our theory is incomplete. And here, at the heart of the black hole, we understand why. In that infinitesimal point, an enormous mass is crushed into a quantum-sized space. This is where the two monarchs meet. This is where the king of the large gravity is forced to operate on the scale of the queen of the small. And what does quantum mechanics have to say about this? It tells us that nothing can be a perfect point. The uncertainty principle forbids it. A particle's position and momentum can never be known with perfect accuracy. The subatomic world is inherently fuzzy, a place of probabilities, not certainties. So, what is the singularity? Is it the infinitely dense point predicted by the smooth equations of relativity? Or is it a fuzzy, chaotic ball of quantum foam, as the laws of the small would demand? The truth is, we don't know. When we try to apply the equations of both theories to this single problem, they give us gibberish. They contradict each other. The pillar of relativity crumbles into infinity. The pillar of quantum mechanics has no language to describe the behavior of gravity. Our two greatest descriptions of reality, when faced with the most extreme object in the universe, are rendered powerless. They fail completely. Our second journey is not through space, but through time itself. We must rewind the cosmic clock. We know our universe is expanding. Galaxies are flying away from each other as the fabric of space-time stretches. This means that in the past, everything must have been closer together. If we run the movie of the cosmos in reverse, we see galaxies merge, stars dissolve into a hot plasma, and the entire observable universe contract into a space smaller than a single atom. Just like with the black hole, general relativity makes a terrifying prediction. It predicts that 13.8 billion years ago, everything, all matter, all energy, all of space and all of time was compressed into a singularity, a beginning of infinite density and infinite temperature, the Big Bang. Once again, Einstein's theory predicts an infinity, a point where its laws break down. It describes what happened a microsecond times after times the beginning with stunning accuracy, but it cannot describe the moment of creation itself. It has no power at time zero. And once again, quantum mechanics objects. The entire universe in that first moment was a quantum system. It was the ultimate realm of the small where uncertainty and probability must have reigned supreme. Was the birth of our universe really a singular deterministic point, or was it a quantum event, a fluctuation in some pre-existing void, a bubble of space-time popping into existence from the cosmic foam, governed not by certainty but by chance? Was our universe born, or was it a statistical inevitability? We cannot answer this question, because to do so we would need a single theory that can speak both languages. A theory that can describe the crushing force of gravity on a quantum scale. A theory that unites the world of the very large with the world of the very small. We need a theory of quantum gravity. This is the holy grail of modern physics. It is the deepest, most profound challenge ever faced by science. To find it is to complete the revolution that began with Newton and was advanced by Einstein. It is to finally understand the fundamental operating system of reality. And for the past half-century, this quest has consumed the lives of thousands of the brightest minds on Earth, dividing the world of theoretical physics into two colossal warring camps. It is a conflict of ideas, a battle of mathematics, a clash of philosophies over the very nature of existence. In one corner, we have the heir to Einstein's legacy of beautiful unifying mathematics, an idea of such breathtaking ambition that it claims not only to unite gravity and the quantum world, but all the forces of nature into a single elegant framework. This is string theory. It makes a staggering proposition that if you could zoom in on a fundamental particle, an electron or a quark, you would see it is not a point at all. You would see that it is a tiny vibrating filament of pure energy, a string. And just as a violin string can vibrate at different frequencies to produce different musical notes, these cosmic strings, by vibrating in different patterns, produce all the different particles and forces we see in the universe. The electron is one vibration, the photon is another. The graviton, the particle of gravity, is another still. In this view, the universe is not made of particles. It is a symphony, a grand cosmic vibration echoing through space-time. It is a theory of almost unimaginable mathematical beauty, but one that comes with a startling price to work. It requires the existence of hidden dimensions, extra spatial directions curled up so tightly that we have never perceived them. In the other corner stands a rival philosophy, a more direct and rebellious approach. This is loop quantum gravity. Its proponents looked at the schism between the two great theories and decided the problem wasn't with the particles, but with the stage itself. They argued that Einstein's great mistake was assuming that space-time was a smooth, continuous fabric. The quantum world, they remind us, is not smooth. It is discrete. It is chunky. So they asked, what if space-time itself is quantized? What if we zoomed in on the fabric of space past any conceivable magnification? We wouldn't see a smooth sheet. We would see a network, a shimmering tapestry woven from finite indivisible loops, atoms of space, pixels of reality. In this view, space is not an empty backdrop for events to unfold in. Space-time is times the events. There is no stage, only the actors. There is a smallest possible area, a smallest possible volume, and therefore no possibility of a singularity. A black hole's core cannot collapse to an infinite point because there are no points. There is only the smallest possible unit of space, and it can be crushed no further. The Big Bang was not a beginning from nothing, but perhaps a big bounce, the rebound of a previous collapsing universe. These are the two titanic contenders in the war for the fabric of space. String theory, the sweeping symphony that seeks to unify everything, but requires a universe far stranger than we can imagine. Loop quantum gravity, the gritty rebellion that seeks to build reality from the ground up, one quantum loop at a time. This is more than a dispute over equations. It is a battle for the soul of physics. It pits those who believe in a final, elegant, unified vision against those who believe in building reality from its most fundamental granular components. The journey ahead will take us to the edge of human imagination. We will explore hidden dimensions, parallel universes, and the very birth of time. We will meet the brilliant, obsessive, and often combative minds behind these two great theories. And we will confront the ultimate question: what is our universe truly made of? Is it a song of vibrating strings, or is it a tapestry woven from quantum loops? The answer, whichever it may be, will redefine our place in the cosmos forever. The war for reality has begun. What if the universe at its most fundamental level is lying to you? What if the two greatest triumphs of human intellect, the twin pillars upon which all of modern physics rests, are built upon a foundation of mutual contradiction? For nearly a century we have lived with this profound and unsettling truth, a truth so deep it cleaves our understanding of reality in two. On one side we have the majestic, sweeping epic of general relativity, Albert Einstein's masterpiece, a theory that describes the universe on the grandest of scales. It is a story of planets bending the fabric of space-time, of galaxies performing a silent gravitational ballet across billions of years of light itself being forced to bow before the immense authority of mass. It paints the cosmos as a smooth, continuous, predictable canvas, a cosmic tapestry woven from space and time. It is perfect. It works every single time we test it. On the other side, we have the strange, paradoxical, and utterly brilliant world of quantum mechanics. This is the story of the universe at its most intimate, its most granular. It governs the frantic, unpredictable lives of the particles that build our world. It's a reality where nothing is certain, only probable, where particles can be in multiple places at once, existing in a ghostly superposition until the moment we look. It is a realm of quantum leaps and shimmering fields, the rulebook for the atom, the engine of the stars. And it too is perfect. The predictions of quantum theory are the most precise and rigorously tested in the history of science. Two pillars, two masterpieces, and they cannot coexist. They despise one another. In our daily lives, they simply ignore each other, ruling their separate kingdoms without conflict. General relativity manages the planets, the stars, the colossal structures of the cosmos. Quantum mechanics flawlessly choreographs the subatomic realm of electrons and quarks. The cosmic king and the quantum jester hold court in separate castles, and for the most part peace reigns. But there are places in the universe where these two kingdoms are forced to collide. Places of such extreme violence and unimaginable density that the very laws of physics are pushed to their breaking point. Plunge into the heart of a black hole. Here, a star many times the mass of our sun is crushed by its own gravity into a point of zero size and infinite density, a singularity. This is the domain of general relativity. It is the ultimate expression of gravitational power. But it is also a quantum domain, an immense mass compressed into a space smaller than any subatomic particle. Here, the two great theories must speak to one another, and when they do, the conversation is a catastrophe. The elegant, flowing equations of Einstein begin to sputter and seize. The numbers they produce climb without limit, screaming towards infinity. The smooth fabric of space-time, once so reliable, tears itself apart into a nonsensical foam of paradox. The theory simply breaks. It is not an error in our calculations. It is a scream, a howl of protest from the mathematics itself, telling us that our understanding is profoundly, fundamentally incomplete. We see the same crisis if we rewind time all the way back to the very first instant of creation, the Big Bang. The entire observable universe, all the matter and energy that would one day form our planet, and 100 billion galaxies was compressed into a point of unimaginable heat and density. It was a quantum object of cosmic proportions. And once again, when we try to use our theories to describe that primordial genesis, they collapse into the same chaotic mess of infinities. They offer us no insight, no window into that first ferocious moment. It is the greatest unknown, a wall beyond which our physics cannot see. This is the chasm. This is the crisis that has haunted physics for generations. It is a gaping wound in our knowledge of the universe. We know with absolute certainty that there must be a deeper theory, a more fundamental description of reality that can bridge this impossible divide. A theory that can speak the language of both gravity and the quantum, uniting them into a single, coherent, and beautiful whole. For physicists, this is the ultimate prize, the holy grail, a quantum theory of gravity, a theory of everything. The first clue to solving this cosmic mystery came not from a deliberate quest for unification, but from a place so unexpected, so seemingly unrelated that it was almost completely overlooked. It emerged from the messy, chaotic, and violent world inside the atomic nucleus. During the 1000, 960 seconds, physicists were wrestling with the strong nuclear force, the incredibly powerful glue that binds protons and neutrons together inside an atom. This force was a puzzle. As they smashed particles together in powerful accelerators, they discovered a veritable zoo of new, exotic, short-lived particles. There seemed to be no rhyme or reason to it, just a bewildering array of masses and spins. They needed a new mathematical framework to bring order to this chaos. A brilliant young physicist named Gabriele Veneziano, while sifting through old mathematics textbooks, stumbled upon a forgotten 200-year-old equation called the Euler beta function. In a flash of insight, he realized it perfectly described the scattering data of these nuclear particles. It was a bizarre, almost magical coincidence. No one knew why it worked, but it did. This discovery ignited a flurry of research. Physicists tried to understand the physical meaning behind this mysterious formula. What was it actually describing? The mathematics seemed to be modeling these elementary particles, not as zero-dimensional points, which had been the standard assumption for all of history, but as something else, something with structure, something that could wiggle and oscillate. The math was describing tiny one-dimensional filaments of energy. It was describing strings. The idea was radical, and at the time aimed squarely at the strong force. The theory proposed that quarks, the constituents of protons and neutrons, were not points, but were connected by these energetic strings like cosmic rubber bands. The tension in these strings held the particles together. For a time, this early version of string theory seemed promising. It explained some features of the nuclear zoo, but it was also plagued with problems. It made strange predictions, including the existence of a particle that had no mass, and most bizarrely of all, that the universe must have 26 dimensions to be mathematically consistent. It was just too weird. It didn't seem to match reality. As a competing theory called quantum chromodynamics came along and explained the strong force with stunning success, string theory was unceremoniously abandoned. It was relegated to the dustbin of physics, a beautiful but failed idea. A mathematical curiosity, but a handful of physicists couldn't let it go. They were captivated by its deep and unusual mathematical elegance. Two of them, John Schwartz and Michael Green, continued to toil in obscurity, chipping away at the theory's inconsistencies. They spent years refining the mathematics, trying to tame its wild predictions, and in the process they stumbled upon something extraordinary. One of the theory's most embarrassing flaws had been its insistence on predicting a massless particle. In the world of the strong force, such a particle simply didn't exist, making the theory seem fundamentally wrong. But Schwartz and his colleagues looked at this unwanted particle again. They calculated its properties, its spin, its interactions, and they realized it had the precise mathematical identity of the one particle that had been missing from the quantum world for 50 years, the graviton. The hypothetical quantum carrier of the force of gravity. This was a revelation of seismic proportions. The theory they had been trying to build to describe the tiny world inside the atom had entirely by accident produced the key to describing the largest force in the cosmos. It was a breathtaking intellectual leap. String theory was not a theory of the strong force at all. It was something infinitely grander. Gravity was not something you had to painstakingly add into the theory. It was an inevitable and natural consequence of the mathematics. It fell out unbidden from the theory's core structure. This accidental discovery, this beautiful mistake, triggered what became known as the first superstring revolution. Suddenly, physicists around the world dropped what they were doing and flocked to this resurrected idea. The theory had been reborn, transformed from a failed model of nuclear physics into the most promising candidate we have ever had for a theory of everything. So, what is it truly telling us about our universe? The central idea is as simple as it is profound. If you could zoom in on any particle, an electron in your fingertip, a photon of light from a distant star, a quark churning inside a proton, you would not find an infinitesimal point. Instead, you would find a single solitary object, a minuscule vibrating filament of pure energy, a string. And just like the string on a cello, it can vibrate in different ways. It can resonate at different frequencies. These different modes of vibration are what we perceive as the different particles of nature. An electron is just a string vibrating in one particular pattern. A photon is the same kind of string, just vibrating in a different pattern. A quark is yet another vibrational mode. The entire menagerie of particles that make up our world, the particle zoo that once seemed so complex, is revealed to be nothing more than the different musical notes, the different harmonics of a single fundamental cosmic string. This is an idea of breathtaking elegance. It's a vision of the universe as a grand cosmic symphony. All the richness and complexity we see around us, the formation of stars, the chemistry of life, the very light that allows you to see emerges from the melodic interplay of these impossibly tiny vibrating strands. The laws of physics in this view are not a disparate collection of rules, but are instead the principles of harmony governing this celestial music. The forces of nature, too, are unified within this framework. When two strings interact, they can join and split. An electron string, for example, might emit a photon string. This interaction, this joining and splitting of vibrating filaments, is what we perceive as the electromagnetic force. The same principle applies to the strong and weak nuclear forces. They are all just different aspects of the same underlying stringy geometry. Every force, every particle, every interaction in the known universe is unified into a single, elegant and coherent picture. They are all just music. And what of gravity, the breakdown that started our entire quest? In string theory, gravity is not a force in the traditional sense. It is just another note in the symphony. That massless particle that fell out of the original equations, the graviton, is simply the string vibrating in its lowest, most fundamental energy state, a pure, simple, unadorned note. This means gravity is woven into the very fabric of the theory from the outset. It is not an afterthought. It is a requirement. Because these strings are objects that exist and move through space-time, they must obey the rules of relativity. And because they are quantum objects, they must obey the rules of quantum mechanics. As a result, string theory doesn't just describe quantum gravity, it times is times a theory of quantum gravity. It is the first mathematical framework ever conceived that naturally and seamlessly marries Einstein's world with the quantum realm. When you use strings to calculate what happens at the heart of a black hole or at the moment of the Big Bang, the infinities that plagued our old theories simply vanish. The mathematics no longer screams. The string, because it is not a zero-dimensional point, has a tiny but finite size. This inherent fuzziness smooths out the catastrophic infinities at the quantum scale, smearing the paradoxes into resolution. It is like replacing the infinitely sharp tip of a needle with the soft pad of a finger. The fabric of space-time is no longer punctured. It is healed, but this profound elegance comes at a startling price. A price that challenges our most basic intuition about the reality we inhabit. For the mathematics of string theory to work, for its equations to be consistent and free of paradoxes, it makes a bizarre and non-negotiable demand. The universe cannot have only the three dimensions of space, length, width, and height, and one of time that we experience. It must have more. The most consistent versions of the theory, known as superstring theory, require that space-time possesses a staggering 10 dimensions. 6 extra spatial dimensions hidden from our view, curled up and compactified at every single point in our familiar space. It's a concept that is almost impossible to visualize. Imagine an acrobat walking on a high wire. From the perspective of the crowd below, the wire is a one-dimensional line. The acrobat can only move forward or backward. But for a tiny ant standing on that same wire, there is a second dimension, the circumference of the wire. The ant can move forward and backward, but it can also walk around the tiny curled-up dimension of the wire's girth. String theory proposes that our universe is like that high wire. We, the lumbering acrobats, are only aware of the 3 vast dimensions we can move through. But at every point in our space, curled up to a size far smaller than an atom, exists another 6-dimensional space, a complex and intricate geometry known as a Calabi-Yau manifold. These hidden dimensions are the arena in which the strings themselves live and vibrate. And the precise shape, the specific geometry of these curled-up dimensions is not just a curious detail, it is everything. The exact way these extra dimensions are twisted and folded determines the fundamental physics of our universe. It dictates the ways the strings can vibrate. It sets the values of the physical constants like the mass of an electron and the strength of the forces. The shape of this hidden microscopic origami defines the very character of our reality. Our universe is the way it is because of the specific geometry of its hidden dimensions. Here we stand before a vision of reality of almost unimaginable scope and beauty, a theory that resolves the greatest conflict in modern science, uniting all forces and all matter into a single kind of entity, a vibrating string. A framework that heals the paradoxes of black holes and the Big Bang, offering us a glimpse of a reality deeper than we ever thought possible. It suggests that our entire universe, with all its vastness and complexity, is just one possible melody being played in a 10-dimensional cosmic orchestra. The mathematics is intoxicating. Its power to unify is unparalleled. It seems on the surface to be the final beautiful answer we have been searching for, the perfect theory. But as we peer closer, as we begin to question the intricate details of this magnificent structure, we find that the elegant symphony begins to reveal disconcerting notes of its own. Is this truly the voice of nature we are hearing, or is it merely the siren song of a beautiful, seductive, but ultimately untestable mathematics, leading us not to the truth, but to an infinite landscape of possibilities from which we can never escape? But for all its breathtaking elegance, for all its mathematical allure, the symphony of strings is not the only performance in town. In the quiet back rooms of theoretical physics, far from the grand orchestral stages of extra dimensions and supersymmetry, a different kind of music was being composed. It was not a symphony played upon a pre-existing stage, but a raw, percussive rhythm that sought to build the stage itself, beat by fundamental beat. A rebellion was brewing, a profound intellectual insurgency against the very foundations upon which string theory was built. This challenger doesn't ask what the universe is made of. It asks a far more radical question. What if the stage, the very container of reality we call space-time, is not a stage at all? What if it too is just another actor? This is the defiant declaration of loop quantum gravity. To understand its power, you must first unlearn what you think you know about space. String theory, for all its complexity, still presents a familiar, intuitive picture. It describes fundamental objects, the strings vibrating and moving times within times, a background of space and time. That background is smooth, continuous, and absolute, like a pristine canvas upon which the cosmic story is painted. Loop quantum gravity looks at that canvas and sees a fiction, a convenient illusion that has held physics captive for centuries. It proposes that if we are to truly unite Einstein's vision of gravity with the bizarre rules of the quantum world, we cannot simply add new quantum ingredients into the classical container of space-time. We must have the courage to take the container itself and shatter it into its quantum components. The revolution of LQG is that it seeks to quantize gravity by quantizing geometry itself. Imagine you are trying to describe a shirt. String theory would be akin to describing the exotic multi-dimensional threads from which the shirt is woven. Loop quantum gravity, however, isn't interested in the threads, it's interested in the weave. It argues that the very properties of the fabric, its texture, its shape, its ability to bend and fold, arise not from a pre-existing sheet, but from the intricate interlocking pattern of the loops that constitute it. There is no background fabric, there is only the weave. LQG is the theory of the cosmic weave. It begins not with matter, but with the pure abstract mathematics of connections, the very relationships that define proximity and dimension. It starts with two of the most powerful ideas ever conceived, quantum mechanics and general relativity, and it takes them both at their word, forcing them into a direct and brutal confrontation. From Einstein's general relativity, it takes the most profound insight of all background independence. This was Einstein's masterstroke, the revelation that space-time is not a fixed arena, but a dynamic, malleable entity shaped by the presence of mass and energy. Gravity, he showed us, is nothing more than the curvature of this active space-time fabric. From quantum mechanics, LQG takes the core principle of granularity, the irrefutable discovery that energy, light, and charge all come in discrete, indivisible packets called quanta. Light is not a continuous stream, but a shower of photons. Energy in an atom is not a smooth dial, but a series of distinct steps on a ladder. LQG then asks the ultimate question. If everything else in the universe is quantum, why should space and time be any different? What if space-time itself is not a smooth, continuous sheet, but a pixelated, granular structure? This is where the 12 theory gets its name. When physicists like Abhay Ashtekar, Lee Smolin, and Carlo Rovelli performed this radical quantization of Einstein's equations, something extraordinary emerged from the mathematics. Space at its most fundamental level resolved itself into a network of abstract links and nodes. These are the famous loops of loop quantum gravity. These are not loops of string moving times through time-space. These loops' times are time-space. They are elemental threads of the gravitational field, quantum excitations of geometry itself. Think of it as a celestial wiring diagram, a cosmic scaffolding constructed from pure relational information. Where two lines in this diagram meet, we have a node. This node represents a quantum of volume, a fundamental, indivisible atom of space. The lines connecting these nodes are the links, and they represent quanta of area. This is a breathtaking departure from our everyday experience. To LQG, if you were to magnify a region of empty space down to the Planck length, a scale so small that an atom is to it, as you are to the entire Milky Way galaxy, you would not find a smooth, empty void. You would find a chaotic, roiling network of interconnected loops, a seething quantum foam. This network is called a spin network. It is a ghostly, abstract graph where the links and nodes are decorated with quantum numbers known as spins, which dictate the size of these fundamental units of area and volume. An area in our universe, like the surface of your hand, is not a continuous surface. It is literally built from an immense number of these fundamental pixel-like quanta of area, each one carried by a link in the spin network piercing through it. The volume of the room you are in is the sum total of all the discrete, indivisible quanta of volume represented by the nodes of the network contained within it. Space in this view is no longer a pre-existing emptiness waiting to be filled. It is an emergent property, a statistical average of the interactions of countless trillions of these quantum loops. The very concept of location becomes relational. A node is not times at times a point in space. The convergence of links, times at times a node, times creates times the point. There is nothing between the links of the spin network, just as there is nothing between the pixels on a television screen. The network doesn't live in space. The network times is times space. This idea is so counterintuitive, so utterly alien to our classical minds, that it represents one of the deepest philosophical divides in all of science. It suggests that the smooth, continuous world we perceive is a macroscopic illusion, a high-resolution rendering of an underlying digital reality. And what of time? If space is a static network, a single snapshot of geometric relationships, then time in loop quantum gravity is the process of that network transforming. Imagine the spin network as one frame in a cosmic movie. The next frame shows a slightly different configuration of loops and nodes. Time, therefore, is not a smooth, flowing river. It is a discrete sequence of quantum leaps, a staccato ticking of the universal clock, where the entire geometry of the cosmos reconfigures itself from one Planck moment to the next. The history of these transformations, the evolution of a 3D spin network through the fourth dimension of time, creates a structure called a spin foam. If a spin network is a diagram of the quantum state of space, then a spin foam is the quantum history of space, a shimmering four-dimensional tapestry of geometric events, where nodes become lines and links become surfaces. In this framework, time itself is emergent, born from the ceaseless, frenetic dance of relational change. Here then we arrive at the central battlefield, the irreconcilable difference that defines the war for the fabric of space. It is the principle we have been building towards the very soul of Einstein's theory of gravity, background independence. String theory in its most common formulations is background dependent. To make its equations work to describe how its strings vibrate and interact, it must begin by assuming a pre-existing stage, a fixed, non-dynamical background of space and time, often a 10-dimensional anti-de Sitter space, or a Calabi-Yau manifold. The strings dance upon this stage, but they do not create it. The geometry of this background is an input, a choice made by the physicist, not an output of the theory itself. To many, this is string theory's original sin. It is a betrayal of Einstein's deepest lesson that geometry is not a static backdrop but the central dynamic character in the cosmic drama. It is like trying to understand a whirlpool by describing the water molecules while ignoring the vortex itself. Loop quantum gravity, by its very construction, is aggressively, proudly background independent. There is no pre-existing stage, there is no fixed geometry, there is no external coordinate system to tell you where you are. The spin network itself times the geometry. The relationships between the loops and nodes define the curvature of space, and the transformations of the network define the flow of time. The stage and the actors are one and the same. This is a universe that literally pulls itself up by its own quantum bootstraps. It is a self-creating cosmos where the laws of physics do not operate times in time, space and time, but rather give rise times to time, space and time through their own quantum interactions. This is a direct, undiluted inheritance of Einstein's vision translated into the language of quantum mechanics. It is the ultimate realization of a relational universe where everything that exists, space, time, matter, energy, is defined purely by its relationship to everything else. To grasp the magnitude of this schism, consider the problem of a black hole. In string theory, one might try to describe a black hole by figuring out how strings behave in the intense gravitational field prescribed by a fixed background geometry. It's a powerful approach that has yielded profound insights, particularly into black hole entropy. Loop quantum gravity, however, attacks the problem from the inside out. It asks, what is the quantum geometric structure that times creates times the black hole's gravitational field? It describes the black hole's event horizon not as a smooth surface in a pre-existing space, but as a dense weave of the spin network's links. The theory then calculates the entropy, the information content of the black hole, by literally counting the number of ways these quantum threads of area can be woven together to create a horizon of a specific size. The fact that this bottom-up calculation, born from a completely different philosophy, produces a result that perfectly matches the predictions of Stephen Hawking is considered one of LQG's most triumphant successes. This fundamental difference in approach, adding quantum things to a classical background versus building a quantum background from scratch, colors every aspect of the two theories. String theory is a theory of unification. It seeks to show that all the different particles and forces we see are merely different vibrational modes of one underlying object, the string. It is a top-down approach, starting with a grand, unified principle and working down to the phenomena we observe. Loop quantum gravity is a theory of quantization. It doesn't try to unify matter and forces in the same way. Instead, it takes the two pillars of modern physics, general relativity and quantum mechanics as they are, and focuses on the single monumental task of reconciling them in a mathematically rigorous, background-independent way. It is a bottom-up approach, building reality from the most basic, indivisible quantum units of geometry. So, the battle lines are drawn, etched into the very fabric of reality they seek to describe. On one side, we have a universe of almost musical elegance, a 10-dimensional cosmos filled with the harmonic vibrations of unimaginably tiny strings. It is a theory of stunning mathematical power, offering a tantalizing, unified vision of all of creation, yet it remains tethered to a classical fixed background that feels like a ghost of a bygone era. It is a beautiful sculpture, but one that stands upon a pedestal it did not carve. On the other side stands a universe of rugged, granular construction woven from a chaotic foam of pure relational information. It is a theory that embraces Einstein's deepest principle of background independence with uncompromising fidelity, offering a picture of a truly emergent, self-creating cosmos. Yet its path to incorporating the full spectrum of particles and forces from the standard model remains more challenging, more uncertain. One theory paints a picture of a grand, unified symphony playing out on a vast, silent stage. The other describes a frantic improvisational jam session, where the musicians, the instruments, and the concert hall itself erupt into existence with every single note. They are two profoundly different answers to the same ultimate question. They represent two competing souls of physics, the drive for unified elegance versus the demand for fundamental consistency. One is a theory times of times quantum gravity that happens times in times space-time. The other is a theory times of times quantum space-time itself. And as we stand at this fork in the road to reality, we must confront the most pressing question of all. How do we choose? In a realm so far removed from our ability to directly see or measure, how can we ever hope to know which of these majestic, warring visions is the true portrait of our universe? And so we arrive at the frontier, a place where abstract mathematics and elegant equations are forced to confront the most violent and enigmatic objects in the known universe. For all their conceptual beauty, for all the promise they hold, both string theory and loop quantum gravity must ultimately face the crucible, the ultimate stress test for any theory of reality. They must face the singularity. This is not merely a technical challenge. It is a battle for the soul of physics. A singularity is a point of infinite density, of infinite gravity, a place where the equations of general relativity scream into nonsense and our understanding of the cosmos simply shatters. It is the breakdown of physical law itself. We find this mathematical monster lurking in two terrifying places, at the heart of every black hole and at the very beginning of time in the Big Bang. A true theory of everything, a genuine map of reality, cannot have holes in it. It must be able to walk into these zones of infinite terror and walk out with coherent, finite answers. It must tame the infinite, and it is here in their radically different strategies for taming this beast that the two contenders draw their deepest battle lines. Let us first venture toward the gravitational leviathan, the black hole, an object so dense that it punches a hole in the fabric of space-time, a one-way door from which not even light, the fastest thing in existence, can escape. At its center lies that dreaded singularity, a point of zero volume and infinite density. For decades, this was not just a puzzle, it was a profound paradox. In the 1970 seconds, Jacob Bekenstein and Stephen Hawking discovered something astonishing. They found that black holes have a temperature, they radiate energy, and most shockingly of all, they possess entropy. Entropy, as we've come to understand it, is a measure of hidden information, a count of all the possible internal arrangements of a system's components. A hot gas has high entropy because its atoms can be arranged in countless ways. A perfect crystal has low entropy because its atoms are locked in a rigid, predictable pattern. But if a black hole has entropy, what precisely are its internal components? What are the microscopic states that this entropy is counting? General relativity provides no answer. It says a black hole is perfectly smooth, described only by its mass, its spin, and its charge. It has no hair, no features, no internal parts to arrange. It is a cosmic vault with a label on the outside telling you its entropy, but when you open it, you find it's utterly empty inside. This is where information itself seems to perish. If you throw a book with all its intricate information into a black hole, that information, according to Hawking's initial calculations, is scrubbed from the universe forever. This violates one of the most sacred tenets of quantum mechanics, that information can never truly be destroyed. This is the black hole information paradox, a deep and troubling contradiction at the very heart of physics. Into this arena of contradiction, string theory makes its grand entrance, not with a single simple answer, but with a breathtakingly new vision of what a black hole even is. We must leave behind the old picture of a simple, empty gravitational pit. In string theory's world of 11 dimensions, the universe is filled with more than just tiny vibrating strings of energy. It is also populated by vast, higher dimensional surfaces, cosmic membranes known as D-branes. Imagine them as immense invisible canvases upon which the open-ended strings of standard particles paint their existence. These branes can be enormous, even universe-sized, or they can be compact and localized. And it is through the intricate physics of these D-branes that string theory offers a stunningly concrete solution to the black hole's mystery. By modeling a specific type of black hole as a complex intersecting configuration of these D-branes, Wrapped up tightly in the extra hidden dimensions, string theorists were able to perform a landmark calculation. They could, for the first time, count the number of ways the fundamental strings and branes could arrange themselves to produce the properties of that black hole. They were, in essence, counting the microscopic quantum states, the fundamental atoms of space-time that constituted the black hole's interior. The result of this monumental calculation was historic. The number they found, the entropy derived from this microscopic stringy description, matched the Bekenstein-Hawking formula derived from pure general relativity and quantum field theory perfectly. It was a jaw-dropping moment of unification. The abstract concept of black hole entropy suddenly had a physical basis. The cosmic vault wasn't empty after all. It was woven from a tapestry of strings and branes humming with quantifiable information. This success led to an even more revolutionary idea, one that has shaken the foundations of physics, the holographic principle. It suggests that everything that falls into a black hole, all the information contained within its three-dimensional volume, isn't lost at all. Instead, it's perfectly preserved, encoded on the two-dimensional surface of its event horizon, much like a three-dimensional image is encoded on the two-dimensional surface of a hologram. What you perceive as the interior of the black hole may be a grand illusion, a projection from a lower dimensional reality written on its boundary. According to string theory, the black hole doesn't destroy information. It stores it on a cosmic hard drive of unimaginable density. The singularity at the center may not even be the final word. Some models, like the fuzzball proposal, suggest that the classical singularity is replaced by a tangled, messy ball of strings and branes, a quantum object that has a real physical size and structure, thereby preventing the infinite collapse. In this first great confrontation, string theory appears to score a major victory. It provides a microscopic model for entropy, offers a compelling escape route from the information paradox, and dissolves the singularity into a complex but comprehensible quantum system. It's an elegant, powerful, and deeply satisfying narrative. But the battlefield is about to shift from the isolated darkness of a single collapsed star to the incandescent blaze of creation itself. We now turn our gaze from the end of things to the absolute beginning, the Big Bang. And here in the shadow of cosmic dawn, loop quantum gravity prepares its counteroffensive, offering a vision so completely different, so fundamentally opposed, that it threatens to rewrite the entire story of our origins. The standard Big Bang model, the bedrock of modern cosmology, tells a story of a universe that emerged from a state of unimaginable heat and density some 13.8 billion years ago. As we rewind the cosmic clock, we see everything in the universe rushing together, galaxies converging, stars merging, matter and energy being compressed into a smaller and smaller volume. Follow this logic to its ultimate conclusion, and you arrive once again at a singularity. A point of zero size and infinite temperature, the origin of space-time and all the laws of physics. But just like the black hole singularity, this is a sign that our theory, general relativity, has broken down. It is the edge of our knowledge. For decades, physicists have sought a quantum theory of gravity precisely to understand what really happened at this moment of genesis. Did time truly have a beginning? String theory, for all its power, has a somewhat ambiguous relationship with this primordial moment. While there are intriguing string-based cosmological models, like the ekpyrotic scenario, which posits our universe was born from the collision of two branes in a higher dimension, many of its frameworks still operate within the general assumption of a hot, dense beginning, not entirely dissimilar from the classical Big Bang. The initial singularity remains a formidable, if potentially solvable, challenge. Loop quantum gravity, however, does not seek to solve the singularity. It seeks to obliterate it. It claims the singularity never existed in the first place. This is not a minor adjustment, it is a revolution. Remember, in LQG, space itself is not a smooth, continuous background. It is a granular atomic fabric woven from discrete loops of gravitational fields. There is a smallest possible unit of area, a smallest possible unit of volume defined by the Planck length. You simply cannot compress space into a point of zero size any more than you can keep folding a piece of paper in half forever. There is a fundamental limit, a final, indivisible quantum of space. As we approach what we once called the Big Bang singularity, this quantum nature of space-time becomes dominant. As the contracting universe is crushed down to this fundamental Planck-scale density, the fabric of space-time itself begins to push back. Imagine a coiled spring. The more you compress it, the stronger its repulsive force becomes. In the cosmology of LQG, the quantum geometry of space-time acts like an incredibly powerful cosmic spring. When the matter and energy of a contracting universe reach the maximum possible density that quantum space allows, a new force, a repulsive force born from the very graininess of space-time, takes over. It becomes so powerful that it overwhelms the crushing pull of gravity. The collapse is halted. The universe does not fall into a singularity. Instead, it rebounds. This is the heart of the LQG cosmology, the Big Bounce. Our Big Bang was not a beginning from nothing, but a moment of transition, a violent rebound from a previous cosmic era. Our universe, according to this breathtaking vision, was born from the ashes of a predecessor, a universe that existed before ours, which collapsed under its own gravity, compressed to the quantum limit, and then bounced back to begin a new cycle of expansion. This is a complete paradigm shift. It replaces the singular linear story of creation with an eternal cyclical one. Time does not have a beginning. The universe has no starting point. It is a cosmic heartbeat, a cycle of collapse and rebirth, stretching back into an infinite past and forward into an infinite future. The singularity, that point where physics died, is healed. It is replaced by a bridge, a quantum tunnel connecting one phase of the cosmos to the next. Our entire observable universe, all the galaxies, stars, and life within it, could be the result of a rebound from a black hole in a parent universe, a seed of cosmic rebirth. The implications are staggering, not just for physics, but for our entire philosophical understanding of existence. It suggests a universe without a moment of creation, a cosmos that has always been and will always be in one form or another. Here, the conflict between the two theories becomes stark, almost visceral. String theory, with its D-branes and holographic principles, provides a compelling, information-rich picture of the black hole interior, resolving one type of singularity with a complex quantum object. Loop quantum gravity, with its atomic space-time, provides an equally compelling but utterly different picture of cosmic origins, resolving the primordial singularity with a great rebound. They are not just offering different mathematical techniques, they are presenting us with two fundamentally irreconcilable histories of reality. One is a story that still broadly aligns with a singular genesis event, albeit one governed by the physics of strings and extra dimensions. The other is a story of an immortal, pulsating cosmos, a story that erases the very concept of a day one. Crucially, this clash is not doomed to remain in the ethereal realm of pure mathematics. The Big Bounce hypothesis makes predictions subtle but potentially detectable. If our universe is the product of a bounce, the violent transition from a collapsing phase to an expanding one would have left faint imprints, specific scars on the largest observable structure we can see, the cosmic microwave background, radiation, the afterglow of our own hot early universe. Loop quantum gravity cosmologists are calculating the precise nature of these signatures. They predict subtle anomalies, specific patterns in the temperature fluctuations and polarization of this ancient light that would be the telltale echoes of a pre-existing cosmos. They are phantom signals from a universe that died to give birth to our own. Finding such an echo would be a profound discovery, lending powerful, perhaps irrefutable evidence to the LQG worldview. Its absence, on the other hand, would strengthen the case for inflationary models more naturally accommodated by string theory. The cosmic microwave background has become the ultimate observational arena, a celestial document upon which the two great theories might one day see their conflicting predictions put to the ultimate test. So, the war for the fabric of space now rages on two fronts. In the isolated darkness of the black hole, string theory has painted a masterpiece of quantum information, but in the primordial fire of creation, loop quantum gravity has offered a narrative of cosmic reincarnation that challenges the very meaning of a beginning. Two stories of the singularity, two vastly different universes. And as we now move from the theoretical battlefield to the experimental frontier, the search for a deciding piece of evidence, A single observation to crown a victor becomes the most urgent quest in all of science. And so, for a breathtaking moment, we glimpse the promise of a final theory, a universe woven from the resonant hum of infinitesimal strings, or one built from a granular lattice of quantum loops. Each vision is a monumental achievement of the human intellect, a testament to our relentless drive to comprehend the cosmos. They offer us elegant, almost poetic solutions to the deepest paradoxes of existence, promising to unite the warring kingdoms of the very large and the very small under a single coherent law. The equations sing with a profound, almost mystical beauty. They whisper of a hidden order, a fundamental logic underlying all of creation, from the fiery birth of a star to the silent dance of subatomic particles. But this is where the symphony begins to falter. This is where the soaring promises collide with the stubborn, unyielding silence of the universe itself. For all their mathematical grandeur, for all their conceptual power, both string theory and loop quantum gravity are haunted by profound, perhaps even fatal spectres of doubt. They are like magnificent unfinished cathedrals, their spires reaching for the heavens, but their foundations resting on ground that has yet to be fully secured. The war for the fabric of reality, it turns out, is not just fought between these two opposing ideas. It is an internal war, a struggle waged within each theory against its own deepest contradictions and its most glaring omissions. The path to a final theory is not a straight line, but a treacherous labyrinth, and we now find ourselves standing before its most formidable walls. For string theory, the first crack in its immaculate facade is not a subtle mathematical flaw, but a crisis of overwhelming, paralyzing possibility. It is a problem so vast, so staggeringly immense, that it has been given a name as epic as the challenge it represents the landscape. To understand it, you must first grasp what string theorists mean by a vacuum. It is an empty space. A vacuum is the ground state of the universe, its lowest possible energy level, the stable configuration from which the laws of physics as we know them emerge. The specific way the extra 6 or 7 dimensions of string theory are curled up their unique geometric shape, their Calabi-Yau manifold, determines this ground state. It dictates the fundamental constants, the masses of particles, the strengths of forces. It sets the stage for our entire reality. The theory's initial hope was that its equations would lead to a single unique shape for these hidden dimensions, a single vacuum state that would mathematically predict the universe we see with its specific value for the force of gravity and the precise mass of the electron. It was meant to be the ultimate prophecy, a set of equations from which our cosmos would emerge, not as a matter of chance, but of mathematical necessity. What physicists found instead was a nightmare, a disaster of choice. The equations did not yield one unique solution. They yielded a multitude, an avalanche. The number is so colossal it defies human intuition, a 1 followed by at least 500 zeros. 10 to the power of 500 possible ways for the extra dimensions to be curled, each one creating a different vacuum, a different universe with its own unique set of physical laws. This is the string theory landscape, a cosmic continent of possibilities with a mountain range of 500 valleys, and our universe is just one tiny, unremarkable patch of grass in one of them. Imagine searching for a single grain of sand, not on all the beaches of Earth, but on a trillion Earths. That is the scale of the problem. The theory that was supposed to explain why our universe is the way it is now seems to suggest that almost any times universe is possible. A universe with no gravity, it's in the landscape. A universe with 94 fundamental forces and 1,000 types of quarks, it's probably in there too. The landscape transforms string theory from a predictive science into a work of cosmic anthropology. It can describe a near infinity of possible cultures or universes, but it cannot explain why we live in this specific one. It loses its predictive power, the very soul of the scientific method. If your theory predicts everything, it predicts nothing at all. This curse of possibility is perhaps the single greatest philosophical and practical challenge facing the string paradigm. It opens the door to the unsettling anthropic principle, the idea that our universe has the laws it does simply because, if it had different laws, we wouldn't be here to observe them. For many physicists, this is a profound retreat, a surrender of the ultimate goal to explain not just how the universe works, but why it must work in the way it does. The landscape suggests there may be no ultimate why, only an endless, terrifying menu of cosmic options. But even if we could somehow navigate this dizzying landscape and find our own cosmic address, string theory faces another, more immediate problem: a complete and utter lack of direct evidence. The theory makes two extraordinary cornerstone predictions about the nature of reality. The first is the existence of extraspatial dimensions curled up into shapes so fantastically small they are invisible to our most powerful instruments. The second is a radical new symmetry of nature known as supersymmetry, or SUSY. Supersymmetry proposes that every fundamental particle we know has an invisible, heavier superpartner, a ghost in the machine of the standard model. Every quark should have a squark, every electron a selectron, every photon a photino. This isn't just an aesthetic addition, it's a mathematical necessity woven into the very fabric of most string models, helping to stabilize their equations and tame violent quantum fluctuations. For decades, physicists believed these superpartners were the key. They were not just a theoretical requirement, but a tangible prediction, a thread hanging from the higher dimensional tapestry that we could finally pull. Their discovery would be the smoking gun, the definitive proof that we were on the right path. The hopes of a generation were poured into the Large Hadron Collider at CERN, a 27-kilometer ring of superconducting magnets designed to be a window into creation. Here, particles would be smashed together at nearly the speed of light, recreating for a fleeting instant the ferocious energies of the early universe. In these fireballs of pure energy, it was hoped the heavy superpartners would finally materialize their fleeting existence, captured by cathedral-sized detectors. It was to be the moment of revelation. Scientists watched their screens sifting through the debris of trillions upon trillions of collisions, searching for the telltale signature of a selectron or a squark, and they found nothing, only silence. The expected signals, the shadows of this supersymmetric world, failed to appear. Not a single one. Year after year, as the LHC pushed its energies higher and higher, the silence only deepened. The absence of supersymmetry is a deafening blow. It doesn't kill string theory outright. Proponents can argue the superpartners are simply heavier, their masses beyond the reach of even the LHC, but it strikes at its heart. It's a prophecy that has spectacularly failed to come true, leaving the theory adrift, its primary anchor to the experimental world seemingly severed. The same story holds for the extra dimensions. Physicists have searched for their effects in subtle ways, looking for tiny deviations in the law of gravity at very short distances, or for energy leaking out of our known dimensions during high-energy collisions. Once again, the results have been relentlessly disappointingly normal. Our universe, as far as we can tell, behaves as if it has only the three spatial dimensions we know and love. Without supersymmetry and without extra dimensions, string theory is left as a magnificent mathematical castle floating in the clouds with no visible bridge to the solid ground of observation. The third and perhaps most intrinsic challenge is woven into the mathematical language of the theory itself. String theory in its current form is a perturbative theory. This is a technical term for what is essentially a profound limitation. It means its equations are approximations. They work incredibly well when strings are weakly interacting, vibrating gently in a calm, flat background of space-time. Using this method, physicists can calculate the probabilities of strings scattering off one another, a process that should correspond to the particle interactions we see. But this is like being able to describe only the gentle ripples on the surface of an ocean. The theory in this formulation cannot describe the ocean itself during a hurricane. It breaks down completely in regions of extreme gravity and high energy, precisely the domains it was invented to explain. It cannot describe the crushing singularity at the heart of a black hole. It cannot describe the universe in its first fiery moments after the Big Bang. In these realms, the interactions become too strong, the curvature of space-time too violent. The approximations collapse into mathematical nonsense, yielding infinite probabilities that signify the theory's breakdown. What is missing is a complete, non-perturbative formulation of the theory, a master set of equations that describes the behavior of strings under any conditions. Physicists believe such a theory exists. They call it M-theory. It is a shadowy 11-dimensional framework that is thought to unify all the different versions of string theory. But M-theory itself is a profound mystery. We have only fragmentary glimpses of its structure, like finding a few beautifully carved stones from a lost city. We do not have the blueprint. We cannot write down its fundamental equations. Without this complete formulation, string theory remains a sketch, a powerful and suggestive collection of ideas and techniques, but not a final coherent theory. It has given us profound insights into quantum gravity, black holes, and pure mathematics, but it cannot yet answer the ultimate questions it set out to solve. It stands before the gates of the Big Bang and the black hole singularity, holding a key that frustratingly, infuriatingly refuses to turn. The Strings song is beautiful, but it is an unfinished symphony, its most crucial movements yet to be written. If the symphony of strings falters on these notes, does the quantum rhythm of space itself offer a more coherent melody? We turn now to its great rival, loop quantum gravity, a theory built not on exotic ingredients like extra dimensions or supersymmetry, but on a stark minimalist reimagining of space and time themselves. Here, the armor also seems impenetrable at first glance. It offers a mathematically rigorous, background-independent picture of quantum spacetime. It makes a concrete prediction that space is not continuous, but granular, made of indivisible atoms of volume, and it beautifully resolves the problem of the Big Bang singularity, suggesting not a beginning from nothing, but a big bounce from a previous cosmic era. Yet, as we draw closer, we see that this contender too bears deep and troubling scars from its own internal battles. Its foundations, while solid in the realm of pure gravity, begin to tremble when confronted with the full, messy reality of the universe. The first and most persistent criticism leveled against loop quantum gravity is its profound difficulty in incorporating the rest of physics. The theory in its purest form is a quantum theory of spacetime geometry and nothing more. It provides a stunningly detailed blueprint for the stage, the quantum spin network structure of space, but it has no natural role for the actors. The familiar particles of our world, the electrons, quarks, photons, and neutrinos of the standard model of particle physics, are not intrinsic to the theory. They don't emerge naturally from the weaving and braiding of the fundamental loops. Instead, they must be added in by hand, coupled to the geometric scaffolding of spacetime in a way that feels awkward and artificial. It is like trying to force the characters of one play onto the set of a completely different one. This is a stark contrast to string theory, where particles are simply different vibration modes of the same fundamental object, the string. In that picture, matter and the forces that govern it are unified from the very beginning. Loop quantum gravity, however, begins with a deep schism between the dynamics of geometry and the dynamics of matter. Bridging this gap has proven to be a monumental challenge. While researchers have developed ways to place the fields of the standard model onto the spin network background, the interactions are notoriously difficult to calculate, and the process lacks the elegant unification that a final theory ought to possess. The theory struggles to explain times why times we have the specific family of particles we do, or why the fundamental forces have their measured strengths. It offers a radical new vision for the fabric of reality, but remains strangely silent about the threads that make up the tapestry itself. Without a natural and compelling way to incorporate matter, loop quantum gravity remains an incomplete picture of the world. It is a theory of the quantum stage, still waiting for its players to arrive. This problem, known as the matter problem, stands as a formidable barrier preventing the theory from making a direct claim to being a true theory of everything. It's a theory of gravity, but perhaps not a theory of reality. The second great hurdle for loop quantum gravity is a problem of scale. The theory provides a beautiful description of spacetime at the fantastically small Planck scale, where reality is a frenetic, bubbling foam of quantum geometry. And we have Einstein's general relativity, a flawless description of the smooth, gently curving spacetime of our macroscopic world of planets, stars, and galaxies. The critical test for any theory of quantum gravity is to prove that the former seamlessly becomes the latter when you zoom out. This is the semi-classical limit, the requirement that the strange laws of the quantum world must reproduce the familiar classical laws at large scales. A digital photograph is made of pixels, but from a distance it looks like a smooth, continuous image. Loop quantum gravity must demonstrate that its pixels of space and time behave in exactly the same way, blurring together to recreate the familiar continuous world of Einstein. This has proven to be fiendishly difficult. The mathematics involved in averaging over the near-infinite complexities of the quantum spin network to recover the gentle curves of a planetary orbit is staggering. For years, physicists have struggled to show that their fundamental theory can reproduce even the simplest law of gravity, Newton's inverse square law, in a clear and unambiguous way. While significant progress has been made with promising calculations suggesting that the theory is on the right track, a complete and rigorous proof remains elusive. The connection between the quantum micro-world of loops and the classical macro-world of Einstein is more like a narrow, treacherous rope bridge than a grand multi-lane highway. Without this solid connection, loop quantum gravity risks becoming a mathematically beautiful but physically isolated island disconnected from the vast continent of known tested physics. It is a potential description of a universe, but until it can be proven to be a description of our times universe at the scales we can observe, it remains a brilliant conjecture rather than a confirmed reality. It must not only explain the quantum origin of the universe, it must also explain the simple fall of an apple from a tree, and that second task has proven to be just as hard as the first. Finally, loop quantum gravity faces a subtle but deeply unsettling challenge to the very foundations of modern physics, a principle held sacred for over a century: Lorentz invariance. This is the cornerstone of Einstein's theory of relativity, the profound idea that the laws of physics are the same for all observers regardless of their constant velocity. Whether you are standing still or flying past in a spaceship at 99% the speed of light, your experiments will yield the same results. It means there is no absolute rest, no preferred frame of reference in the cosmos. But loop quantum gravity is built upon the idea of a smallest possible length and a smallest possible area, the Planck length. This discreteness, this fundamental pixelation of reality, seems to create a special preferred scale. It suggests a kind of ultimate cosmic grid, an absolute rest frame for the fabric of space itself. If this were true, an observer moving very fast relative to this grid might see the world differently. They might, for example, see high-energy particles of light traveling at slightly different speeds depending on their energy. This would be a catastrophic violation of Lorentz invariance, unraveling the entire tapestry of special and general relativity. It would be like discovering that the speed of light is not a universal constant, but something that depends on how you are moving. The theory does not necessarily have to violate this principle. The quantum nature of the grid could be more complex, preserving the symmetry in a subtle way, but the danger is very real and the mathematics is incredibly complex. Physicists have looked for evidence of this potential violation, studying the light from distant cataclysmic cosmic events like gamma-ray bursts. If space-time were granular in this simple way, high-energy photons from these explosions should arrive at our telescopes slightly later than low-energy photons, having been slowed down by the bumpy texture of space over their journey of billions of years. The search has been relentless, and the results, once again, a profound silence. The universe appears to be unnervingly perfectly smooth. The speed of light seems to be truly absolutely constant. This lack of evidence for Lorentz violation puts loop quantum gravity in a difficult position, forcing its proponents to find more sophisticated ways to construct the theory so that its fundamental discreteness does not break the most sacred symmetry in physics. So the two titans stand locked in a struggle not only with each other, but with the ghost of incompleteness that haunts their own magnificent equations. String theory, with its curse of infinite possibility and its frustrating lack of evidence, loop quantum gravity with its awkward separation of space and matter and its unresolved relationship with the classical world, neither can claim victory, neither can be dismissed. They are flawed, brilliant, and maddeningly incomplete. The clean lines of the battle have dissolved, revealing a far more complex and uncertain landscape. The war for the fabric of space is not a simple duel between two champions, but a desperate search for a truth that seems to lie just beyond the reach of both. This stalemate, this period of profound uncertainty, has forced a question upon the world of physics. Have we reached the limits of our old ways of thinking? And if both of these paths are blocked, where in the vast wilderness of ideas do we go from here? And so we find ourselves here at the precipice of a great intellectual divide. On one side, a cosmos woven from the impossibly fine vibrations of strings, singing their silent symphony in a grand theatre of hidden dimensions. On the other, a reality built atom by atom from space itself, a granular quantized tapestry where geometry is not a stage, but a dynamic, evolving actor in the cosmic drama. This schism, this deep and seemingly intractable chasm between our two best hopes for a final theory, can feel like a failure, a roadblock on our quest to understand everything. But what if we have been looking at this all wrong? What if this is not a war to be won, but a message to be deciphered? Physics has been here before, standing at a crossroads of contradictions. We once wrestled with the ghost-like nature of light, which behaved as a wave one moment and a particle the next. The resolution was not to choose one over the other, but to embrace a new, deeper reality, quantum mechanics, where such duality was not a paradox, but a fundamental truth. Perhaps the perceived war between strings and loops is a similar signpost pointing toward a synthesis, a more profound framework that holds both of these magnificent ideas as partial truths. The thought is tantalizing, a whisper of reconciliation that has inspired a small but fiercely dedicated group of theorists to become bridge builders, searching for common ground in this contested territory. They are the diplomats in this war of ideas, and their work is among the most challenging and speculative in all of science. One of the most audacious paths toward peace begins deep within the labyrinth of string theory's own mathematics. Recall that its original formulation required a fixed, pre-existing stage of spacetime, a rigid background on which its strings could dance. This was the very feature loop quantum gravity was built to eliminate, insisting that spacetime must emerge from the theory itself, not be assumed by it. For decades, this difference, background dependence versus independence, formed an uncrossable border between the two nations of thought. But string theory has evolved. The discovery of M-theory revealed a richer, stranger landscape, one populated not just by strings but by higher dimensional objects called brains, vast membranes that could be as large as an entire universe. Within this sprawling, almost baroque structure, some physicists believe they have found a clue, a way to build the stage from the actors themselves. The idea is breathtakingly ambitious. Could a vast collection of these fundamental brains, interacting and overlapping in the complex geometry of M-theory, somehow conspire to create a state that is indistinguishable from a universe with no pre-existing background? Could their collective quantum behavior weave the very fabric of space-time, much like trillions of individual water molecules, each with no inherent liquidity, collectively give rise to the fluid-flowing nature of an ocean? In this picture, loop quantum gravity's spin networks would not be the enemy. Instead, they might be an emergent phenomenon, a description of what this collective state of strings and brains times looks like, times at the Planck scale. The smooth, continuous world of strings, when viewed through a particular mathematical lens, might resolve into the discrete, pixelated reality of loops and nodes. It would be like looking at a masterful impressionist painting. From a distance, you see a continuous flowing image of a water lily pond. But as you step closer, you realize it is composed of thousands upon thousands of discrete individual dabs of paint. Neither view is wrong. They are simply different descriptions of the same reality at different scales. Could string theory be the distant, sweeping view, and loop quantum gravity in the intimate, close-up examination of the brushstrokes? This potential connection is not a proven theorem, but a tantalizing research program, a thread of hope that one theory might contain the other within its boundless architecture. It suggests that rather than being rival empires, one might be a detailed map of a single province within the other's vast dominion. But there is another potential bridge, one that comes from a completely different direction, arising from the deepest mystery in all of physics, the black hole. When we tried to understand the information that falls into a black hole, we stumbled upon one of the most bizarre and powerful ideas ever conceived, the holographic principle. It tells us something that defies all intuition. It suggests that everything happening inside a volume of space, every particle, every field, every intricate event, can be fully and completely described by information encoded on its two-dimensional boundary. It's as if you, your home, your entire city could be nothing more than a complex hologram projected from a distant surface. This principle first emerged with concrete mathematical footing from string theory in a famous discovery known as the ADS CFT correspondence. This correspondence is a precise mathematical dictionary, a Rosetta Stone that translates the physics of gravity inside a volume of space-time into the language of ordinary quantum field theory living on its boundary. It is a stunning, proven link between two worlds that seemed utterly separate. And here in this holographic dictionary, peacemakers see their greatest opportunity, because loop quantum gravity in its own way is also profoundly holographic. Its fundamental structures, the spin networks, are graphs that describe the quantum state of space itself. When these spin networks puncture a surface, like the event horizon of a black hole, they endow it with a discrete quantized area. The physics of the volume is intrinsically tied to the degrees of freedom living on its edge. So here we have it. Two completely different theories born from antithetical philosophies, both independently discovering a version of this radical holographic idea. Is this a mere coincidence, or is it the clue we've been searching for? Could the holographic principle be the common language, the shared syntax that allows us to finally translate between the elegant prose of string theory and the stark, powerful poetry of loop quantum gravity? Perhaps the true theory of quantum gravity is inherently holographic, and strings and loops are merely two different attempts to describe the projector and the projection. Two different ways of reading the cosmic hologram. This work is pushing the boundaries of what we understand about space-time and information itself. It forces us to confront the possibility that the universe we experience in all its three-dimensional glory might be an elaborate illusion, a grand projection from a simpler, flatter reality. And yet, for all their mathematical splendor, for all their philosophical beauty, these attempts at unification remain conjectures, elegant specters, haunting the halls of theoretical physics. Both string theory and loop quantum gravity, whether at war or in search of peace, exist in a cathedral of pure thought built from the ethereal bricks of mathematics alone. To become physics, to become a true description of our world, they must eventually step out of the cathedral and face judgment. They need an arbiter, an ultimate impartial judge, and in science, that judge is always unequivocally experiment. The grand challenge, the frustration that has haunted both fields for a generation, is that the scale at which their predictions become obvious. The Planck scale is so small, so fantastically energetic, that we have no hope of probing it directly. We cannot build a microscope powerful enough to see a quantum of space. We cannot build a particle accelerator powerful enough to create a superstring. So how do we choose? How does nature cast its vote? We must become cosmic detectives searching for faint, indirect fingerprints left behind by these hidden realities on a scale that we can times observe. We must listen for the faintest whispers from the dawn of time and search for the most subtle tremors in the fabric of the cosmos. Our first great listening post is the universe itself observed through the new window of gravitational waves. These ripples in space-time, first detected in 2015, are the closest thing we have to a cosmic nervous system. They are disturbances that travel directly from the most violent events in the universe, colliding black holes, merging neutron stars straight to our detectors on Earth. They are pristine messengers, unaltered by the billions of light years they have crossed. And within their subtle waveforms there may be clues. Loop quantum gravity, with its granular structure of space, makes a startling, though incredibly subtle prediction. It suggests that space-time might behave like a prism, not for light, but for gravitational waves themselves. High-frequency waves might travel at a slightly different speed than low-frequency waves, a phenomenon called dispersion. The effect would be infinitesimally small, but as a wave travels across the entire universe, that tiny difference could accumulate. If we were to ever detect a gravitational wave signal from the edge of the visible cosmos, and find its shape slightly smeared out in a predictable way, It would be the first tangible evidence that space-time is not a smooth continuum, that it is indeed built from discrete quantum bits. String theory offers its own set of potential signatures. If fundamental strings exist, some of them could have been stretched to cosmic size during the explosive expansion of the early universe. These cosmic strings, thinner than a proton, but with the mass of a mountain range per inch, would still whip through the universe today. If two were to collide, or if one were to snap, it would unleash a burst of gravitational waves with a unique, unmistakable character, a sharp cusp in the signal that our detectors are actively searching for. Furthermore, the collision of two black holes in a universe with extra dimensions as predicted by string theory might produce a different gravitational wave ring down the fading vibrations after the merger than a collision in our familiar 4 dimensions. LIGO, Virgo, and future space-based observatories like LISA are our gravitational ears pressed against the door of reality, listening for these telltale signs. Every chirp they detect is a new page of data to be scoured, a new opportunity for one theory to finally break its silence and speak. Our other great hope is a fossil, the oldest relic in existence. It is the light from the Big Bang itself, the cosmic microwave background radiation. This faint afterglow which permeates all of space is a baby picture of the universe taken when it was just 3,800,000 years old. Imprinted upon that ancient light are the seeds of all future structures, tiny fluctuations in temperature and polarization that grew into the galaxies we see today. Those fluctuations were born in the first fiery moments of creation, the very crucible where quantum gravity reigned supreme. Both strings and loops paint different pictures of that primordial state. They make subtly different predictions about the precise statistical patterns of those fluctuations, about the way the light is polarized, and about the presence of primordial gravitational waves from that era. With every new satellite we launch, with every improvement in our telescopes, we are examining this photograph with a more powerful magnifying glass. We are hunting for a non-Gaussian anomaly, a specific polarization mode, times any times deviation from the standard cosmological model that might bear the unique signature of stringy physics or a loopy bounce instead of a singular big bang. So far, the universe has kept its secrets well. The evidence remains stubbornly out of reach, a ghost in the machine that we know must be there but cannot yet grasp. This has led some to question the entire enterprise, to label string theory and loop quantum gravity as philosophy or mere mathematics rather than science. But this misses the profound importance of the struggle itself. This war has been one of the most productive failures in the history of science. In trying to bridge this divide, we have been forced to invent entirely new fields of mathematics. We have been forced to reconsider the very nature of space-time information and reality. The questions being asked by these physicists, by these brave explorers of the impossibly small, are the deepest questions we can ask as a species. Where did it all come from? What are the fundamental rules? What is the true substance of the world we inhabit? The conflict is not a sign of failure. It is a sign of our relentless, unyielding, and deeply human curiosity. It is the engine of progress, the creative tension that is pushing us beyond the comfortable shores of known physics into a vast, uncharted ocean. The final answer may not be strings or loops. It may be something else entirely, a concept so strange and beautiful that we have not yet developed the language to describe it. But whatever that final answer is, its discovery will have been built upon the foundations laid down in this great intellectual struggle, this magnificent ongoing war for the fabric of space. And so the front lines of this colossal intellectual war fall quiet. The echoes of vibrating strings and the quantum hum of space-time loops fade into a contemplative silence, leaving us here at the very edge of what is known. We have journeyed through a conflict fought not with armies but with equations, a struggle for the soul of reality itself. You have witnessed two of the most audacious, most profound ideas ever conceived by the human mind, locked in a decades-long contest to claim the ultimate prize, a true theory of everything. On one side, string theory with its breathtaking ambition. It offered us a universe of sublime, almost musical elegance, a cosmos where every particle, every force, every tremor of existence is but a different note played on a single infinitesimal filament. This was the Grand Orchestra, a vision of unity so complete, so mathematically resonant it felt as though it had times to be true. It promised to dissolve the jarring dissonance between the two great pillars of modern physics, uniting the colossal warping universe of Einstein with the frenetic, uncertain dance of the quantum world. To achieve this harmony, it asked us to accept a radical new cosmos, one with hidden dimensions curled up into unseen geometries, a landscape of possible universes so vast it defies imagination. It gave us a language, a powerful new mathematics, that seemed to connect disparate islands of physics, a Rosetta Stone that could in principle translate the laws of gravity into the laws of particles. We saw how this theory, in its relentless pursuit of consistency, birthed concepts that have reshaped science far beyond its original scope. The holographic principle, the idea that all the information in a volume of space could be encoded on its boundary, was a stunning revelation, a gift from the arcane mathematics of string dualities. It suggests that you, me, and everything we perceive might be a projection from a distant, lower dimensional surface, a cosmic hologram painted on the edge of space-time. This idea alone, an unexpected treasure unearthed during the string theory gold rush, has forced a fundamental re-evaluation of what information reality and even space itself truly are. String theory became more than just a theory of quantum gravity. It evolved into a sprawling theoretical framework, a vast continent of mathematical ideas whose coastlines we are still mapping. Yet, for all its power, it remained tethered to a classical stage. Its shimmering strings and undulating brains performed their cosmic ballet upon a pre-existing fixed background of space-time, an assumption that left many feeling it had missed the deepest lesson of relativity. On the other side of the battlefield stood loop quantum gravity, the fierce revolutionary, the iconoclast. It took Einstein's most profound insight that gravity is not a force times in time-space-time but the very curvature times of time-space-time, and pushed it to its absolute limit. If space-time is a physical entity, it argued, then it must obey the bizarre, pixelated rules of quantum mechanics. There could be no fixed stage, no quiet backdrop for reality to unfold upon. The stage times was times the actor. This theory did not offer a unified symphony of particles and forces. Instead, it offered something arguably even more radical, the atomic structure of nothingness. It asked you to throw away your deepest intuitions about space and time, to abandon the smooth, continuous fabric we perceive, and to see the universe for what it might truly be: a network. A discrete, finite tapestry woven from elementary quantum loops of geometry, a spin network where each intersection, each node, represents a fundamental, indivisible chunk of volume, where the lines connecting them are the elemental quanta of area. From this perspective, space is not empty. It is a seething computational foam of geometric relationships constantly updating at the Planck scale. Time in this world does not flow like a river. It emerges, ticking into existence through the sequence of these discrete changes, a staccato rhythm at the heart of reality, one quantum moment giving way to the next. Loop quantum gravity gave us a breathtaking glimpse into the quantum heart of a black hole, not as an infinitely dense singularity, but as a Planck star, where gravity becomes so powerfully repulsive that space-time itself bounces back from total collapse. It offered a plausible, tangible mechanism for the birth of our universe, suggesting that the Big Bang was not a beginning from nothing, but perhaps a big bounce from a prior collapsing cosmos. It provided a concrete, background-independent vision of a quantum reality freeing physics from the anchor of a classical space-time. But this freedom came at a cost. Its fierce focus on quantizing geometry left the rest of physics, the particles and forces of the standard model, waiting in the wings. Recreating the smooth classical world of Einstein from its choppy quantized foundations has proven to be an Everest-like challenge, a problem so difficult it is known as the semi-classical limit. So, after this epic war, where do we stand? Who is the victor? The profound and perhaps unsettling answer is that the search for a single winner may be the wrong way to frame the question. This was never a simple war with a clear victor and vanquished. It has been a crucible, a high-pressure environment of intense intellectual competition that has forged our understanding of the universe into something stronger, sharper, and far more nuanced. The true legacy of this conflict is not a final theory, not yet, but the incredible new territory that was mapped by both sides in their quest for the summit. They have acted as twin lighthouses, illuminating the dark oceans of our ignorance from two completely different shores. String theory, with its top-down approach, began with the dream of unifying all of nature, and in doing so discovered powerful new mathematics and principles like holography that have become indispensable tools for all of theoretical physics. Loop quantum gravity, with its bottom-up strategy, started with the established principles of relativity and quantum mechanics, and by taking them seriously constructed a startling new picture of quantum spacetime, forcing us to confront the granular nature of reality. The tension between them, the elegant but background-dependent symphony versus the radical but incomplete quantum geometry, has been enormously productive. It has clarified the essential questions we must answer. Is space-time fundamental or emergent? Are the laws of nature unique, or are we living in one choice among a near-infinite landscape of possibilities? Are there extra dimensions? Is reality continuous or discrete at its most fundamental level? These are the great questions that this war has etched into the bedrock of physics. Without this competition, without the brilliant minds on each side challenging the assumptions of the other, we might never have framed these problems with such stunning clarity. And now, as we look to the horizon, the rigid battle lines of the past are beginning to blur, suggesting the next chapter of this story may not be one of conflict but of synthesis. The future of quantum gravity research may lie in a third way, a new paradigm that emerges from the wreckage and wisdom of this great war. Physicists are now exploring hybrid models, audacious attempts to bridge the conceptual chasm between the two theories. Could the vibrating strings of string theory themselves be woven from the more fundamental loops of loop quantum gravity? Perhaps the brains that shimmer in higher dimensions are not elementary but are collective, states vast continents of interconnected spin networks. Or maybe the holographic principle born from string theory is the ultimate key, providing the mathematical bridge to connect the background-dependent world of strings with the relational background-independent world of loops. These are the nascent whispers of a revolution, the first glimmers of a potential peace treaty, a unified vision that incorporates the most powerful ideas from both camps. But ideas, no matter how beautiful or compelling, are not enough. Physics is not mathematics, it is not philosophy. It is a science, and science demands evidence. This is the monumental challenge that looms over the entire field. We are trying to probe a realm of reality so small, so energetic, that it is almost beyond comprehension. The Planck scale, the fundamental resolution of the universe, is a quadrillion times smaller than a proton. Reaching that scale with a particle accelerator would require a machine the size of our entire galaxy. So where do we look for the truth? How can we ever hope to test these magnificent warring ideas? The answer is that we must learn to listen to the universe with unprecedented sensitivity. We must become cosmic archaeologists, searching for fossilized clues left over from the universe's fiery birth. Perhaps hidden in the faint glow of the cosmic microwave background, the afterglow of the Big Bang are tiny temperature fluctuations, a specific pattern that could only have been imprinted by the physics of strings or the bounce of a loop, quantum cosmos. Or perhaps in the gravitational waves that ripple across the cosmos, from colliding black holes and neutron stars, we might find a subtle signature. A slight dispersion, a tiny variation in the speed of different frequencies that would tell us space-time is not a smooth highway, but a bumpy quantized road. We are searching for a single anomalous photon from a distant cosmic explosion whose journey has been slightly altered by the granular foam of space-time. These are the faint, almost impossible signals we are hunting for. It is a search that will demand new technologies, new observatories, and a level of global collaboration that will push humanity to its limits. And what if we find nothing? What if the signatures of quantum gravity are so faint, so well hidden, that they remain beyond our grasp for another century or even a millennium? Does that mean this entire quest was a failure? Absolutely not. Because alongside the search for physical evidence, Another quieter revolution is taking place, a revolution in the very language we use to describe reality mathematics. Both string theory and loop quantum gravity have been incredible engines for mathematical discovery. They have demanded new branches of geometry, new forms of algebra, new ways of thinking about infinity and discreteness, forcing mathematicians to venture into uncharted territories of abstract thought. This symbiotic dance between physics and mathematics is one of the deepest and most mysterious aspects of the scientific endeavor. Somehow, abstract structures conceived in the pure realm of the human mind turn out to be the perfect language to describe the physical world. It is as if the universe is whispering its secrets to us in the form of equations, and our challenge is to become fluent enough to understand. Perhaps the next great breakthrough will not come from an observatory, but from a mind armed with nothing more than a piece of paper and a pencil, discovering a new mathematical structure that finally unlocks the puzzle, revealing the elegant logic that underpins both strings and loops. This is the enduring hope. The quest for quantum gravity, this grand intellectual war, is ultimately so much more than a search for a final equation. It is a testament to the boundless curiosity and relentless spirit of our species. Think of it, we are creatures evolved on the surface of a single fragile planet, our lives unfolding on scales of meters and seconds. Our brains were shaped by the demands of surviving on the African savanna, not for contemplating the quantum nature of a black hole's interior or the geometry of 10-dimensional space. And yet here we are. We have managed to piece together the story of the cosmos back to its first fractions of a second. We have uncovered the fundamental particles and forces that animate our world with breathtaking precision. And now we stand at the threshold of the final frontier, daring to ask how the entire universe, space, time, matter, and energy came to be. The stories of string theory and loop quantum gravity are the latest, most ambitious chapters in this epic human adventure. They may be incomplete, they may even in the end be wrong, but they represent monumental achievements, towering cathedrals of thought built by generations of brilliant and dedicated minds. They are the architectural blueprints for possible realities, powerful new lenses that have permanently changed how we see our place in the cosmos. The ultimate truth may be one of these theories, or a synthesis of the two, or something so new and so strange that we can't even imagine it yet. But the journey itself has transformed us. The search for the fundamental laws of nature is a mirror reflecting back at us the incredible, almost paradoxical nature of our own consciousness. We are finite beings adrift in an infinite cosmos, yet we are driven by an insatiable need to comprehend that infinity. The war for the fabric of space is far from over. The next generation of physicists, astronomers, and mathematicians are already gathering on the front lines, armed with new ideas, new technologies, and the same unyielding curiosity that has driven us since we first looked up at the stars, and I wondered why. The final answer, whatever it may be, awaits us, out there hidden in the silent mathematics that knits together the cosmos. And the quest to find it, that glorious, frustrating, awe-inspiring quest, is and always will be our greatest adventure.